Okay, I think it's recording. I guess we'll figure out when it's over. Alright, so today we're doing section 2, topic 4. And we basically have learned most of these concepts in section 1. So this should mostly be a review. But today we're just talking about these concepts when we talk about linear functions. Okay? So these notes are from Algebra Nation, but I'm going to teach them to you myself. If you need a more of an explanation, go to Algebra Nation. You'll find these exact same notes, exact same lesson as I'm going to give you, just maybe explained in a different way. Okay? So on that first page, how many x-intercepts does a linear function have? Okay, so I'm going to draw 4 little graphs, and so are you. So that we can help answer this question. Help ourselves to answer this question. And I'm going to also label my axes, the x-axis and the y-axis. The question says, how many x-intercepts does a linear function have? Okay, we know a linear function makes a line, right? So my first example, I'm just going to draw a random line, and I'm not going to put numbers on my line. It's just going to be a random line. Just have yours look similar to mine, okay? And if you don't have a ruler handy, of course everyone has their ID on, so you can just use the edge of your ID. And you know that an x-intercept means what? What does that mean? What's a y-intercept? Where your graph crosses the y-axis. So what is an x-intercept? Where it crosses the x-axis. So in this pink line that I drew, how many times does it cross the x-axis? Just once, right here. So in this example, the question said how many x-intercepts does a linear function have? In this example, it has 1. All right, let's look at another example. I'm going to make a horizontal line that is parallel to the x-axis. How many x-intercepts does this line have? 0 or none, right? It does not cross the x-axis. It does not intersect the x-axis, so it does not have an x-intercept. How about this crazy one? This line is actually on the x-axis. So how many intercepts would I say it has? Somebody was saying it. Infinitely many, right? The line is the x-axis, so it has an infinite number of x-intercepts. How about this one? This one is a trick. How many times does the line cross the x-axis? Once. Don't write that down. The question said, how many x-intercepts does a linear function have? Is this a function? No, why not? Well, it's not a function because it does not pass the vertical line test. Remember, to be a function, your graph can only touch any vertical line at one point, and this graph touches that vertical line in an infinite number of points. So it's a line, but we wouldn't consider it a function. So since the question said how many x-intercepts does a linear function have, this one's not a function. That one was just a big old trick. The next question says, how many y-intercepts does a linear function have? Now I'm going to draw 3 little graphs for this one. And my first one, I'm going to draw a line similar to the one that I did on the first question above. This time the question asked me about y-intercepts. So remember, a y-intercept is where a graph crosses the y-axis. So how many y-intercepts does this function have? Just one. Right here. How about in this example? This is parallel to the y-axis. How many y-intercepts does it have? This linear function. It's not a function. It doesn't cross the y-axis, but it's also not a function. And what if I had a line that actually was on the y-axis? But is it a function? No. If it just said the line, yeah, it'd have an infinite number, right? But it said function. This is not a function. Again, it does not pass the vertical line test. So if it's a linear function, it has to cross the y-axis at some point. Otherwise, it can be a line but not a linear function. All right, next part. Linear functions are either increasing, decreasing, or neither. Sketch graphs of each type. So my first graph, I'm going to sketch an increasing linear function. And remember, we learned in section 1 that increasing means, think about your graphing calculator and the little cursor. As you're moving your little cursor to the right, your x values are increasing as you go to the right, correct? So as you're moving to the right, as x increases, y increases. So a linear function does not change directions. It's either increasing or decreasing. So an example of an increasing function, as I'm going to the right, as x increases, y increases. That would be an increasing linear function. Does that have a positive slope or a negative slope? Or neither? It's a positive slope, right? So what kind of slope do you think a decreasing linear function would have? Negative, because as x increases, y would decrease. So just draw any line with a negative slope. As your x increases, so as you're going to the right, your y decreases. That would give you a negative, I should have written slope on the last one. Slope. The left one was positive slope, the right one was negative slope. Now draw a horizontal line. On this one, as x is increasing, what is y doing? It's not changing, right? It's remaining constant. So this would be neither increasing or decreasing. And the slope of this line is 0. Because if you think about it, slope is rise over run. So if I chose from this point to this point, I have a rise of 0, a run of 3. That reduces to 0. A vertical line is undefined because you have a rise of however many, say 3, in a run of 0, you can't have 0 in the denominator. So vertical line has undefined slope, horizontal line has a slope of 0. But it's neither increasing or decreasing. Now also I wanted to define your end behavior on these as a review. So on your increasing slope, let's define the left side first. So we would say as x is approaching what? On my green highlighted side, what's x approaching? Negative infinity, while y is approaching negative infinity, right? As x is approaching negative infinity, y is also approaching negative infinity. This was part of your tests on section 1. Now let's describe the right side. On the right side, as x is approaching what? Positive infinity, y is approaching positive infinity. That's just a review. For decreasing, let's describe the left side of the graph first. Doing a little color coordinating here. So on the left side, that what I highlighted green, x is approaching what? Where's my x approaching on this side of the graph? Negative infinity. And y is approaching where? Where your y is going? Positive infinity. The right side of the graph, as x approaches, where my x is going on this side, what direction are my x values going? Positive infinity. And y's are approaching negative infinity. Everybody cool with that? We have a question? Okay. Neither increasing nor decreasing. The left side of my graph, what is x approaching as it goes to the left? When it goes to the left, x always approaches negative infinity, but that doesn't mean y does. What is y approaching on the left side of this graph? Is it approaching positive or negative? Neither, right? So we would say y, and I shouldn't have put the arrow there. I would just say y remains constant. As x approaches negative infinity, y remains constant. The right side of the graph, when you're going to the right, your x is always approaching positive infinity. So as x approaches positive infinity, what's y doing on the right side? Remains constant. Everybody cool with that? All right, next page. Which will be the back side. Linear functions can have symmetry about the y-axis, symmetry about the origin, or no symmetry. Sketch graphs of each type. We learned about this in section 1. We did not have it on the test. Remember, we did an algebranation video that describes symmetry and odd functions and even functions and all that stuff. So the first thing we're going to do is draw a line that's symmetrical about the y-axis. So basically that's going to be any horizontal line. So my example is symmetric. About the y-axis. So here's my y-axis. If it's symmetrical about the y-axis, then the y-axis is like the line of symmetry, right? The left side reflects across over the right side across the y-axis. So say I chose a point that's 2 points to the right of the y-axis. If I go 2 points to the left of the y-axis, there's going to be a point there if it's symmetrical. If I choose a point 10 units to the right of the y-axis, if it's symmetrical, there should be a point 10 units to the left of the y-axis on the same line. There is. So we would say that's symmetrical about the y-axis. Okay? Let me draw a line that's symmetrical about the origin. So if it's symmetrical about the origin, it has to go through the origin, which is at 0, 0, and be symmetrical on each side. So if from the origin I went up 1, right 1, to be symmetrical, through the origin I'd have to go back to the origin and go in the opposite direction, down 1, left 1. Or if I went up 2, right 2, to be symmetrical from the origin I would have to go down 2, left 2. Of course, I could use a different slope. If I went up 3, right 1 from the origin, I'd have to go to the origin and go down 3, left 1 to be symmetrical about the origin. And the last one, we're going to do a line that has no symmetry. So we say a line's not symmetrical if it's not symmetrical about the y-axis or about the origin. So pretty much any other line that's not horizontal or symmetrical about the origin. See how that one did not go through 0, 0? So even though it looks like this line just shifted down, it's not symmetrical about the origin. So we would say it has no symmetry or not symmetrical. Either way. Anybody have a question? The next part says, describe the end behavior of a linear function of linear functions with a positive rate of change. So when you're talking about linear functions, rate of change is the same thing as what? What's rate of change talking about? Slope, right? You learned that in Algebra 1. Rate of change is the same thing as slope. So basically, we already answered this question on the previous page. I'm just going to sketch a quick little graph. And I'm just going to draw some random line with a positive rate of change. Same thing as positive slope. And it wanted us to describe the end behavior. We just did this on the previous page. All right? So, this has a positive rate of change. I'll describe my left side first. Quickly, since we've already done this. As x approaches, on the left side, what's my x approaching? Positive infinity or negative infinity? Negative infinity. What's y approaching? Y'all can say it. Just because I'm recording, you can still answer. They won't know who it came from. When my arrow's going this way, are my y values getting larger or smaller? Smaller, so that's negative infinity. The right side of my graph. When your arrow goes to the right, x is approaching what? Positive infinity. And in this case, my y is approaching positive infinity as well. Next question, describe the end behavior of linear function with a negative rate of change. So now I'm just going to sketch any line that has a negative rate of change, which is the same thing when you're talking about lines, is the slope. Negative slope. which we know is it's decreasing. So any old line with a negative slope. Rate of change. Let's describe the left side first. Messy. As x approaches, when you're going to the left, where's x going? Positive or negative infinity? When it's going to the left, x is going to negative infinity. As y is going to where? Positive infinity. On the right side, x is approaching what? Positive infinity as y approaches negative infinity. Everybody cool with that? That's totally a review. The let's practice, second side of your page. Determine the following features of f of x equals 2x plus 5. Okay, and we know f of x is the same thing as y, right? So if you want to think of that as y equals 2x plus 5, same difference. If they use function notation, we know that means this must be a function. It must pass the vertical line test. So the first thing they want to know is the x-intercept. So remember, any ordered pair on the x-axis has a y value of 0, right? So if you want to know where the graph crosses the x-axis, you say, okay, well, when y is 0, what is x? So if we want to find the x-intercept, instead of y, we'll put in a 0 and solve for x. And that will give me the x-intercept. So in this case, I'll subtract 5 from both sides. 0 minus 5 is negative 5 equals 2x. Divide by 2. And x equals negative 5/2, or you could say negative 2.5, or negative 2.5. So that is the x-intercept. So the y-intercept is where your line is going to intersect the y-axis. And if you look at any graph, any ordered pair on the y-axis has an x value of 0. So if you want to know the y-intercept, take your equation and find when x is 0, what is y? That'll be your y-intercept. We did that on last night's homework as well. So take my equation, and instead of 2 times x, I'll do 2 times 0. Notice now the only variable I have is y, so I'm solving for y. So 2 times 0 is 0, 0 plus 5 is 5. My y-intercept is positive 5. Now to answer the rest of these questions, to me, it's going to be easier if I can visualize my graph. So I'm going to sketch a quick graph where my x-intercept is negative 2.5, which I'm going to call negative 5/2, and my y-intercept is positive 5. Question C says it wants us to list the increasing intervals. Remember, increasing is when x is increasing, y is increasing. Do we have any increasing intervals in this example? From left to right, as x increases, what's y doing? Increasing. Does it ever stop and decrease? So my whole thing's increasing, right? So in interval notation, from left to right, I'm describing my x values. So my x values coming from the left are coming from negative infinity, and they're going all the way to positive infinity on my x-axis. So interval notation, from negative infinity to positive infinity, it's increasing. Remember, with infinity or negative infinity, you always use a parenthesis, never a bracket. Because in interval notation, sometimes we use brackets, sometimes we use parentheses. With infinity, you always use parentheses. All right, so where is it decreasing? Does it have a decreasing interval? No, y'all just told me it's increasing the whole entire time, right? A line doesn't stop and change directions. So there are no increasing intervals, or I'm just going to say none. Now, E and F, we have not talked about before. They're easy to confuse. It says positive intervals, negative intervals, okay? That's easy to confuse with increasing intervals and decreasing intervals, all right? They don't mean the same thing. Y'all hear me? Don't mean the same thing. To be a positive interval, different than increasing, it's talking about what part of my graph has positive y values. In other words, it's above the x-axis. So you might want to put a little definition. Positive intervals are above the x-axis, or you could say positive y values. Negative intervals, that's not decreasing, totally different. It means what part of my graph, if any, is below the x-axis or has negative y values. And then any point that's on the x-axis is not positive or negative because it is the x-axis. All right, that's like your boundary for positive and negative. So interval notation, we're describing our x values from left to right. So from here to here, from negative infinity all the way to negative 5.5, would that be a positive interval or a negative interval? From all the way down here, negative infinity, all the way to this point. That's going to be negative interval, okay, because it's below the x-axis. So in interval notation, you describe left to right. From negative infinity on your x-axis all the way to negative 5.5. And I use a bracket because it does not include negative 5.5. At negative 5.5, it's not increasing or decreasing. That is on the x-axis. And then from negative 5.5 all the way to positive infinity, would that be positive or negative? Positive. So start from left to right, from negative 5.5 all the way to positive infinity. That's a positive interval. You see the difference between positive and increasing and negative and decreasing. They're easy to confuse. It's just one of those things you got to memorize. Is this line symmetrical? So remember, for a line to be symmetrical, it's got to be symmetrical about the y-axis or about the origin. If it's neither of those, we say it's not symmetrical. Is this symmetrical? No. No symmetry. Now let me do a little color coordinating over here. So my positive interval, I'm going to highlight in yellow, was that section. And my negative interval, I'll highlight in green. And then when I describe the end behavior, I'll use those same colors, okay? So end behavior for the left side, I'll use that green color. And that says as x approaches, what's the green part of my graph? Where's x going to? Negative infinity. When you go to the left, you're always going to negative infinity on the x-axis. What's y approaching on the green side? Where are my y values going? Larger or smaller? Smaller, so that would be negative infinity. The positive interval side, the yellow side in my case, as x approaches positive infinity, y approaches positive. This side, my x's are getting larger, my y's are getting larger. Everybody cool with that? Okay. Anybody have any questions before I turn my page? Last page. There's a little 42 down the bottom corner. Make sure you're in the right spot. 42. Give an algebraic representation of a linear function for each of the following features. Now, if you were doing this section on your own, we would all have different answers, okay? There's not one particular answer, but that does not mean that anything that you put is correct. That just means there's a whole bunch of different options that you could put. So the first one says, they want us to give an algebraic representation of a line with no x-intercept, okay? To me, for each one of these, I need to draw a line that matches the description and then write the equation from there. That makes more sense to me. So we want a line with no x-intercept. So if it cannot cross the x-axis, then it must be parallel to the x-axis, right? So I'm just going to draw a horizontal line that goes through 3 on the y-axis. Anybody know the line that I drew, what the equation of that line is? Remember, the slope of a horizontal line is 0. So what is the equation of that horizontal line? It's y equals 3. If I went through -3, horizontal line through -3 would be y equals -3. A vertical line is x equals wherever it crosses the x-axis, okay? Otherwise, you got to have a slope and y-intercept in there. All right, I want a y-intercept at 0, -3. So my only limitation is I have to be a y-intercept at 0, -3. Now, I could draw another vertical line, but I'm not going to. I'm going to make a line with a positive slope of 1. So if I go up 3, I would go to the right 3, because that reduces 3 over 3, 1 over 1, right? And that's just going to be easy for me to write the equation. So remember, slope-intercept form is y equals mx plus b. M is your slope, b is your y-intercept. So the equation of the line I drew would be y equals, my slope is what? Rise of 3, run of 3 reduces to what? 1. So my slope is 1x, or my rate of change. What's my y-intercept? Where did it cross the y-axis? -3. That's where it told me to cross, right? And what I write, y equals 1x minus 3? I would just write y equals x minus 3. There are tons of different lines that you could draw with a y-intercept of -3. I was just trying to, since I don't have a graph readily available, I was just trying to do an easy slope, you know, slope of +1. C, no increasing intervals. Well, if you have a line and you can't have an increasing interval, what kind of line could you have? What kind of intervals? Decreasing. So if I have a decreasing interval, just means it's got to have a negative slope. It didn't say y-intercept or anything like that. So I'll just make it go through 0 and have a slope of -1. So in slope-intercept form, my slope is -1x. My y-intercept in this one is +0. or minus 0. It doesn't matter because 0 is not positive or negative. And if I clean that up, that would just be y equals negative x. Again, there's tons of different lines that you could have drawn. I'm just trying to make them basic. Okay, this next part, it's a little confusing. I want to well, actually it's the negative, this one down here, E and F. I want a decreasing interval from negative infinity to positive infinity. Well, look at that line I just drew. Is it decreasing from negative infinity to positive infinity? Yeah. So can I just use that same equation? Sure. Decreasing, not negative. Decreasing. It's decreasing. As x is increasing, y is decreasing from negative infinity to positive infinity. Part E, positive interval from negative infinity to 3. Okay. This part's confusing. Positive means it has to be above the x-axis from negative infinity, so on the x-axis, that's down here, all the way to 3. All right? It's got to be positive. That means coming from negative infinity all the way till you get to 3, you got to be above the x-axis. So if I draw a line, I'm going to make that have a slope of 1. So a rise of 3, a 1, a 3, and technically that would have to be a slope of negative 1. Does that have a positive interval from negative infinity to positive 3? Yes, Miss Rayleigh, it does. And my slope is what? We know it's negative. I have a rise of 3, a run of 3. So that reduces to negative 1. So my slope is negative 1. Put an x with a slope. And what's my y-intercept? Y-intercept is what? Positive 3. So I would write y equals negative x plus 3. It could not have a positive slope because if it was a positive slope and went through positive 3, it would look like this. And that would not be positive from negative infinity to 3. F, you have to have a negative interval. So negative means below the x-axis from positive 5 to positive infinity. So from 5 all the way to positive infinity, it's got to be negative, which means it would be below the x-axis from 5 to positive infinity, right? So if I did a slope of negative 1, that means it would cross my y-axis at positive 5. I know that's a terrible line. It's not straight. It's just hand drawn. So that would be y equals rise of 5, run of 5, and it's negative, reduces to negative 1, so negative x, and my y-intercept is positive 5. And if I wasn't sure about my equation, I could always look at my calculator. We know how to enter an equation, right? If I would have y equals negative x plus 5, look at my graph. Looks like what I drew. So when x is 5, all the way to when x is positive infinity, that section of the graph's below the x-axis, so that means it's negative. Right? I don't know if y'all get what I'm saying or not. Everybody just seems to be staring into space today. Does this make sense? Even though it's a terrible line? Alright. Symmetric about the y-axis. So we know if it's symmetric about the y-axis, basically that's going to be any horizontal line. And I'll just go ahead and have it cross at positive 3 again. So what would that equation be? Y equals 3. H, I want end behavior as x approaches negative infinity. So as the left side of your graph is going to the left, y is approaching positive infinity. So I'll just draw another easy line. as x is approaching negative infinity is y approaching negative infinity in the graph that I drew. Yes, Miss Rayleigh. So this has a y-intercept of 0, and let's say the slope is rise of 1 or run of 1. Would it be positive or negative? Does this have a negative slope or a positive slope? Negative. My y-intercept is 0, so I don't really have to write negative x plus 0. I just go with negative x. Okay? Alright, we're almost finished. Beat the test. Complete the following table by describing key features of linear functions. Linear functions have one x-intercept. Always, sometimes, or never. Think about to that first page of notes. Linear functions have one x-intercept. Always, sometimes, or never. Look at this page. Sometimes. Linear functions have one y-intercept. Look at that page. Always, sometimes, or never. Sometimes. Linear functions are increasing. Sometimes. Sometimes they're decreasing. Sometimes they're not doing either. Linear functions are symmetric about the x-axis. Never. If it's symmetric about the x-axis, it's not a function, right? Because that means it's a vertical line, and vertical lines, it's a line, but it's not a function. So this said linear functions are symmetric about the x-axis. Nope. That's a never. Linear functions are symmetric about the origin. Sometimes. In linear functions, as x approaches positive infinity, y approaches negative infinity. So that would be a line that looks like that. Always, sometimes, or never. Sometimes. You may have questions? All good? Okay. So I will pause the video and give you your assignment. And this again was section 2, topic 4, which is labeled on the front page of those notes. If anything's in here confusing and you want to hear more about it, just go to Algebra Nation, section 2, topic 4. Make sure you're in Algebra 2, and you will find same lesson, someone explaining it differently than I did. Okay.